Alright, hello, my name is Thomas Trifu, and this is my video for Project 2. So to start off, we're going to drag over Fluent, click into Geometry, swap this to 2D, right-click, New Design Modeler. Okay, now we're in Design Modeler, going to click into the XY plane, orient like this, rectangle, start at the origin, dimensions. Alright, the horizontal is going to be 1 meter, and the vertical is going to be 3 centimeters. So horizontal 1 meter, vertical 0.03 meters. Next, click into the sketch, concept surfaces from sketches, apply, generate. Alright, next, go into the mesh. Alright, now our mesh is up. So first thing I'm going to do is name all the sides. This top one I'm going to call the far field. This one on the left, inlet. One on the bottom, wall. And one on the right, outlet. Okay, we're going to click into mesh. We're going to right click, insert face meshing. Click on this, hit apply. Click back into the mesh, right click, sizing now. Click the top and bottom. Hit apply, swap this to number of divisions, and we're going to do 100. And capture curvature, we're gonna set to no. Behavior's hard. Generate. Okay, now that finished meshing, click back into mesh, right click, insert sizing. Gonna click the left and right now. Apply. Number of divisions. This time I'm going to do 1000. Capture curvature, no. Behavior, hard. And we're going to introduce a bias. We're going to introduce this type of bias so that it scales from large chunks, large meshes to smaller meshes, with a bias factor of 20. Yes. And I'm going to reverse the bias on this right one so that they both start with larger mesh pieces, mesh divisions, and go down in size. Now I'm going to hit generate. Alright, now if I click into the mesh and we zoom in, it's very dark, but that's because we have a very fine mesh that starts out relatively thick, and then as it goes down, it gets 20 times thinner, which is exactly what we want. Alright, now I'm on to setup. We're going to click into it. I realized after loading it up that I forgot to update the mesh. So I'm going to go back here, update, and then I can go into my setup. Because I didn't update the mesh, it just opened and there was nothing there. But now there should hopefully be all of the mesh and all the outline on the left present. Okay, now that we're here, first thing I'm going to go to is models. Switch this from SSTK Omega to laminar, hit OK. Results, residuals, going to switch these all to 1E -6, hit OK. Going to go to materials, fluid, air, and I'm going to customize this. Give it a density of 1.2, viscosity of 1.8 times 10 to the -5. Alright, and boundary conditions. The inlet velocity I want to be 2 meters per second. So 2. Alright. The pressure outlet I want to be, let's just prevent reverse flow, change nothing else. And then this far field, I don't want to be a wall. I want it to be a, we'll do pressure outlet. And then prevent reverse flow, nothing else changes. This wall, want to make sure that it is stationary. Great, no slip, wonderful. Reference values. Compute from inlet, reference zone, surface body. Looks good. Scroll down to initialization, click into it, right click, initialize. Alright, it finished initializing. So I'm going to click into run calculation, then double click. Number of iterations, 500 should be good. And let's calculate. Okay, our calculation just finished. Here's my residuals. They struggled for a bit at first, but then they eventually decreased very nicely. Alright, and from here we can go back to Workbench and go into our results. In the results, we're just going to do this and then make some lines. Line 1 is going to be at x equals 35 centimeters, and it's going to go up to, up to the top of it. How many samples? 101 should be fine. Line 2 is going to be the same way. This is going to be 0.75, though. 0.03 again. 101 samples, great. And the third line is going to be, we're just going to make an end line. And it's going to be right before the end, so 99.9 centimeters with 101 samples as well. Alright, great. Now we're going to create a horizontal line, and it's going to go along the wall. So this is actually the right coordinates right here by default. We're going to swap to 501 samples though. And there we go. Next, we're going to create some vectors at the end line. We're going to call this velocity vectors. And it's going to be at the end line. It's going to have a reduction factor of 5. Its color is going to be constant. Let's just make it black. Symbol is arrow 3D with size 0.3. And hit apply. And now we can scroll on in, and you can see these are our velocity vectors at the pretty much the very end of our wall. And you can see the boundary layer here, and then as it approaches the flow velocity u infinity here. Okay. Next, we're going to make some contour maps. So contour 1 is going to be a velocity map camp. And its location is just going to be all of symmetry 1, which is the interior surface. It's going to be velocity u. It's going to have... how many contours should we have? 101 should be fine. And apply. Alright, and you can see a pretty nice, let me just move this legend real quick. Horizontal, fixed. There. You can see the boundary layer starts very small, and then it increases in this this square root type form. It looks like a square root line. Yeah, alright, great. Next we're going to do a pressure map. I'm going to just turn off the velocity map for right now. It's going to be over symmetry 1 again, and it's going to have a lot more contours because otherwise it looks a bit more blocky. So with 501 contours, here is our pressure map. You can see at the head of this plate, it's pretty high pressure, and then it encounters some regions of low pressure here. Don't exactly know why that is. And then it normalizes as it goes out. This purple color is about, it's negative, but it's just under 0. Alright, next thing to do is to create some graphs. So this one's going to be velocity profiles. Velocity profiles, and we're going to use line 1, which is going to be 35 centimeters, and line 2, which is 75 centimeters. The x-axis is going to be velocity u, the y-axis is going to be y, and here's our graph. As you can see, the 35 centimeter one, the boundary layer ends sooner, as predicted by theory. However, you can notice that there is a slight overshoot at this point. Not exactly sure why that is. I'm not sure if it's an artifact of the simulation or why, but it does overshoot the 2 meters per second for u infinity. And then it gradually comes back. Okay, Next is going to be another chart. This one's going to be wall shear. Oh, wall shear chart. And we're going to use that wall line, and this is I'm just going to name it wall. And we're just going to graph X versus wall shear X. And as you can see, starts very high, and then slowly, not slowly, pretty intensely falls off. Okay, and that is also consistent with the theory. This actually just overestimates it at this end, but it gradually converges with the theory as it goes along the x-axis. All right, that's pretty much it for. Oh, one more thing that I need to show is that if you go back to your results here, click into reports, click into forces, you can select the wall and then print, and that will tell you your forces and your coefficients for pressure, viscous, and total drag. You can see there's no pressure drag, and the viscous skin drag coefficient is 3.93 times 10 to the negative 3, which is pretty close to what the theory predicts. All right, that's pretty much it for Project 2. Thank you.